Black holes, wormholes, and time dilation. All concepts of general relativity that Christopher Nolan wove into his 2014 film Interstellar in a manner we had never seen before. While many loved its groundbreaking, scientific take on the dangers of intense time dilation, as his group of astronauts in search of a new home for humanity found themselves losing years in minutes, there were certainly elements of the film and its ending that seemed strange. Towering waves sweeping around planets, black holes that you can enter and use to reach across time and space using gravitational forces. Interstellar at times felt like it strayed from science into science fiction. But what is the science and what is the fiction? What did the film get right? Where did it take artistic license and diverge from our current scientific knowledge? Can you really use a black hole to communicate ideas across space and time? I'm Alex McColgan, and you're listening to the Astrum podcast. Join me today as we learn the truth about Interstellar. We will explore the numerous scientific phenomena of this film that underpin wormholes and black holes, explore the real estate of the Gargantua Pantagruel system, and discover the realities of what happens when you bend space-time to its extreme. For those of you who need a reminder, let's begin with a quick plot recap. In the film, a disease referred to as the Blight takes hold of crops on Earth and starts killing them, causing a population collapse and technological decay as humanity focuses on farming instead of spacefaring. Our protagonist, a former NASA pilot named Cooper, finds himself at a hidden NASA base where they are working on plans to save humanity. Hope has arrived in the form of a wormhole, a tunnel through space-time that they have detected near the orbit of Saturn half a century ago, which is thought to lead to potentially habitable planets. In the film, they show the wormhole not as a cliché portal, but through distortions of stars near Saturn. So here we have our first piece of science to evaluate. This portrayal of a wormhole makes sense. A wormhole is an extreme distortion of the fabric of the universe, similar to a black hole, and would only really be visible through the light near its edges becoming warped. Wormholes are interesting. We have the theory and mathematics behind them somewhat solved already thanks to Einstein and relativity. Wormholes connect space-time to itself, resulting in a shortcut that joins separate points in space and even time to one another. The film uses a classic analogy for this, showing a pencil piercing a shortcut through a piece of paper representing space-time. Sadly though, although we have the theory, we don't actually have the means to make them, even if they can be made at all. There are a couple of problems with wormholes. To begin with, their creation. The scientific advisor for the film, Kip Thorne, released a few physics papers after the film to discuss the scientific advancements they made in its production. In a paper titled Visualizing Interstellar's Wormhole, he notes that it is difficult to create a wormhole out of nothing, as it would require the existence of backwards time travel. You see, once the two ends of a wormhole were linked, they would stay linked. Then, if you could time dilate one end for another by moving it very quickly, causing it to move slower in time than the other end, you could enter the end further along in time and emerge at the point further back in time, thus entering your own past. You could then, for instance, grab yourself and stop yourself from entering the first portal in the first place, creating a paradox where you both enter and do not enter the portal, breaking reality and also my brain. There are lots of mathematical arguments that advocate against this sort of thing, such as Stephen Hawking's chronology protection conjecture. Simply put, it states that the laws of physics would prevent wormholes, these closed time-like curves, from appearing in the first place. Admittedly, this hasn't been proven and relies on a bit of an appeal to common sense. Loops can't exist because we would struggle to imagine how they can exist. This is a problem we return to later in the film. However, the time travel aspect isn't the only problem with wormholes. Traveling through them is theoretically tricky too. You see, if a wormhole were to be created, the throat of the wormhole would soon pinch off and the shortcut through space-time would be sealed due to gravity forcing it to close in on itself. So the moment Cooper tried to enter the wormhole, it would instantly close, ending his mission before it started, which would make for a boring film. To make a wormhole persist long enough that people can travel through it, we would have to use a mathematical hack. We pretend as if some exotic matter exists which has negative mass. This negative mass would then have to be placed at the throat so that it can create opposing curvature, which would counteract the tendency of the wormhole to close, keeping it open in perpetuity. You might be thinking that this sounds made up, and you'd be right. We have never found negative mass, and have no idea how to make it, so this seems like a mere mathematical curiosity. So while wormholes are allowed for in scientific fact, actually traveling through one is so far just science fiction. Still, without it, the rest of the film couldn't really happen, so you can understand why Nolan decided to keep it in. Whether or not this conjecture is true, this backwards causal relationship is baked into the movie. Not just because of the existence of the wormhole which implies it, but also with a reveal at the climax of the film, which we will return to later. Now, let's move on to the next piece of science to evaluate. After the crew makes their way through the wormhole, they arrive near a supermassive black hole called Gargantua. Gargantua is a supermassive black hole some 10 billion light years from Earth and a whopping 100 million times the mass of our Sun. Gargantua, like most genuine black holes we've discovered to date, rotates. It has lots of angular momentum which causes it to spin. As black holes spin, they also boost the rotation of their accretion disk of gas and dust. In Interstellar, this is what provides light and warmth to Gargantua's orbiting planets, Miller and Man. Miller's planet is a water world with knee-deep oceans and 1,200 meter tidal waves. It orbits incredibly close to Gargantua, just on the cusp of the event horizon. But wouldn't this kind of proximity be too dangerous and volatile to be habitable? Is this kind of proximity to a black hole even realistic? Actually, some researchers say it is. They argue these so-called planets wouldn't be so different from planets orbiting stars. But rather than form in a star's protoplanetary disk, they are thought to form in the black hole's accretion disk when ice-covered dust particles collide and fuse. Eventually, they gain enough mass to have a gravitational pull of their own, drawing more and more matter in until a hard planet is formed. Okay, so if planets do exist, what is their space environment like? Well, for starters, black holes emit a lot of radiation, primarily through hot, accreting gas. This accretion power is immense, orders of magnitude more than anything we could get from nuclear fusion. One paper suggests a planet like Miller would be completely surrounded by a 6,000-degree blackbody radiation field. Dr. Thorne, the Nobel Prize-winning physicist who consulted on the film, disagrees. In his book, The Science of Interstellar, he argues instead that Gargantua's disk is comparable in temperature to our Sun's surface, so emits lots of light but little to no X-rays or gamma rays. He also says the accretion disk is super thin and confined to Gargantua's equatorial plane. Such disks are actually possible around black holes that haven't ripped up a star in the last million years or so I suppose the film doesn't actually veer off from reality there. Unlikely, but not impossible. Okay, but how can Miller maintain a stable orbit around a black hole as large as Gargantua? Like planets orbiting our own Sun, Miller's planet has its own motion. If it was going fast enough to escape the Sun's gravity, it would shoot right past. However, if it was going slowly, it would get pulled in entirely by the Sun's gravity. The same is true for Gargantua. A planet in a stable orbit would only be possible if Miller's planet was going fast enough not to be pulled into Gargantua's immense gravitational pull, but not so fast that it shoots right past it. Though this seems virtually impossible, Dr. Thorne hypothesized a sweet spot that could exist where the centrifugal force of the planet balances out the gravitational force pulling it inwards. However, the real issue isn't the planet's orbit, it's the planet's formation. Is it even possible for smaller, slower objects to coagulate together to form a planetary body so close to a black hole? In 2019, a group of physicists showed it is possible, but only if the planet formed within the accretion disk. Dr. Thorne aligns with this in his book and takes it a step further, stating that it's actually not possible for Miller's planet to exist outside the accretion disk. This presents a problem, as in the film, we see the planet orbiting well beyond the accretion disk. It is in the wrong place as far as the physics is concerned. But sometimes you have to take creative license and decide on fiction over fact to get more visually impactful images. Now for our next piece of science to evaluate, let's take a look at what happens when the crew reach Miller's planet. Some of the crew go down onto the planet, but within just a short couple of hours have skipped forward decades into the future, much to the misfortune of the crewmate they left behind, who had to live out those years at normal speed. This part of the film is absolutely plausible. This is gravitational time dilation in action, and is thoroughly proven experimentally. Gravitational time dilation is a result of the bending of space-time caused by massive objects. Time itself runs slower when you are gripped by stronger gravity. It even takes place here on Earth, between us and our orbiting satellites. Much like the crewmate left outside the gravity well experiencing faster time, a clock placed at the orbit of GPS satellites records 45 extra microseconds per day compared to a clock on the Earth's surface. GPS must take this effect into account to get calculations of your position right. If they didn't, your Google Maps location would quickly diverge from your actual position. It's crazy to think that the same underlying theory that explains black holes and time travel also helps us find our way home when we are lost. That in itself is Nobel Prize worthy. Of course, in Interstellar, the time dilation effect is taken to the extreme. In the film, time on Miller passes 60,000 times slower than on Earth. Given where the planet is located, would time dilation actually be this severe? While researching this podcast, I came across differing opinions. Some think yes, it is possible, while others deny it, saying time dilation is only felt once you're inside the accretion disk, much closer than Miller's location in the film. According to Dr. Thorne, for this kind of time dilation to be realistic, Gargantua would have to spin at 1 in 100 trillion parts slower than the maximum spin possible for a black hole of that size. Incredibly unlikely, but technically not impossible. We can't discuss Miller's planet without discussing its waves. Being so close to Gargantua, it is under enormous tidal gravity. Dr. Thorne wrote that this most likely would make Miller's planet football-shaped along its equator, bulging strongly toward and away from the black hole. He also postulates that being this close to the black hole, Miller's planet would have to be tidally locked. I'm not sure how a tidally locked planet would be able to remain a water world. Surely half the world would be ice and the other half super hot. But if we continue the thread from earlier and accept that Miller's planet was meant to be located in the middle of Gargantua's accretion disk, then the heat wouldn't be one-sided anyway. Speaking of water, let's talk about Miller's waves. The film would have you believe that being subjected to such intense tidal forces gives rise to the colossal tidal waves we see on screen. They can be compared to tidal waves here on Earth, which are dictated by our sun's and moon's gravitational forces, but on a much larger scale. Dr. Thorne himself admits that the only way he can make the equations work is by making Miller's planet rock back and forth relative to Gargantua. But that would require a third body very close by, like another large planet, to keep its orbit eccentric. A second theory he proposes is that the tidal forces deform the planet's crust, leading to enormous tsunamis, but that still depends on something rocking the planet. Perhaps the best Miller analog we know of is Jupiter's moon, Europa. Much like Miller's planet, Europa has an eccentric orbit, arising from the gravity of the other Galilean moons tugging on it. This orbit also cracks its crust a lot, and creates tides in its subsurface ocean that stretch and relax the moon's surface. The only thing to nitpick here is the size of the black hole in the sky from the view of the planet. In The Science of Interstellar, Dr. Thorne states that Gargantua is 100 million times the mass of our Sun, and that this would mean that the black hole would take up half of the entire sky of Miller's planet to make the calculations work out. However, Nolan decided to make it look smaller in the sky, so that it would appear more striking when it's the focus of the story later on. Here is an example of where aesthetics won out over true scientific exactitude. There's an interesting story about how the black hole and wormhole were created for Interstellar. Using real equations derived from general relativity, the special effects team created a program called the Double Negative Gravitational Renderer, or DNGR, that can calculate exactly how light beams would pass through distorted spacetime. This is a bit like the ray tracing you see in modern video games. With that technology, computers calculate how rays of light from a source would bounce around the environment, simulating how it would be absorbed and diffused from different surfaces to give a realistic view of the scene. The difference is that with video games, light travels strictly in straight lines between surfaces. With a wormhole, space-time itself is distorted, and the light is made to take curved paths. So the team developed software that could propagate light bouncing off a planet like Saturn, or coming from stars on the other side, and figure out what path it would take to get to a camera. The computer would then generate an image based on what the camera would see. It's really pretty clever. The team generated visuals of wormholes with different lengths. Longer wormholes would give more time and space for light to bounce around, creating greater distortions in the image. In the end, Christopher Nolan decided to choose a model of a very short black hole that would get the point across about how light is distorted, while also not looking too disorienting. This same software was used to model Gargantua, which actually was scientifically groundbreaking. In the words of Interstellar's visual effects scientist Oliver James, the software led to the first time ever, before any other scientist, I saw in ultra high definition what a fast spinning black hole looks like. Using a thin light emitting disk as the standing for the accretion disk of swirling matter around the black hole, they simulated how the light would realistically bend around Gargantua. Have you seen images where above and below the black hole you see the top and bottom of the accretion disk from the far side? The reason for this is because the light has bent all the way around the top of Gargantua due to the distortion of spacetime. They used DNGR to also calculate how the light would be redshifted and blueshifted due to the extreme speeds the matter was traveling at. This would also affect the brightness of the light. In the end, Nolan decided to turn off the redshifting and brightness changes as he felt it would be too much for the audience, and the final version of Gargantua that appears in the film is based on the initial simulation, enhanced with just a bit of lens flare. It's a fascinating example overall of how science really played a massive part in the film's visuals, although apparently not the most important part. Ultimately, this was a film intended to entertain, not specifically to educate. Now, back to our tour. Overall, Miller's planet doesn't seem to be very hospitable at all, as the crew of the Endurance mission would discover. The film got this right, so we follow our protagonist to the next destination. The second planet the Endurance crew visits is Man's planet. It's a harsh, icy world, also orbiting Gargantua, though not quite as closely as Miller's does. There's no mention of time dilation here, but there are other unique features that make this planet fascinating. As we discover through the course of the film, Dr. Mann falsified data to make his planet appear more habitable than it actually was, in order to be rescued by a future crew. He claimed there was a rocky surface below, with breathable air and organic material, though this was never actually found. Instead, the whole planet seems to be a frozen world, a large sponge-like network of ice mountains, caves, and crevices surrounding big voids, with frozen clouds in the upper atmosphere. In order for frozen clouds to remain suspended, they have to be less dense than the atmosphere. Call me a skeptic, but this seems highly unlikely. Dr. Thorne theorizes the clouds are most likely frozen CO2, which has a density of 1.55 grams per centimeter cubed, assuming Earth's atmospheric pressure. An ammonia-rich atmosphere would be closer to 0.00077 grams per centimeter cubed. No chance of floating dry ice in ammonia gas, unless the atmospheric pressure on man is wildly different to where these numbers would change drastically. In any case, the film doesn't go into any explanations about this, so we'll just assume creative liberty was taken here to emphasize the visual differences between Miller's and man's planets. It is thought these ice clouds sublimate, repeatedly freezing and evaporating, then freezing again. It's thought that this could be due to the eccentricity of man's orbit about Gargantua, which causes the planet to heat up and cool off, depending on its distance from the black hole. It seems Nolan took a lot of artistic license with man's planet. Because of this, it's hard to compare it to anything in our universe. So far, we haven't discovered any exoplanets with ammonia-rich atmospheres. We have found plenty of cold exoplanets though. This exoplanet, an icy super-Earth 21,500 light-years away, is one of the coldest known exoplanets we know of, reaching temperatures as low as -220 degrees Celsius. Like man's planet, it is not a good candidate for a human colony. Let's turn our attention to Edmund's planet. After leaving man's planet, Cooper and Brand don't have enough fuel to make it to Edmund's planet, orbiting the star Pantagruel 1 light-year away. After slingshotting around Gargantua at a cost of 51 years due to time dilation, Cooper jettisons himself to shed weight from the Endurance and get Dr. Brand to Edmund's planet. However, it's unclear how Brand would have decelerated into orbit around Edmund's. One option is by slingshotting around another black hole, but this isn't shown in the film. Edmund's is a rocky planet with clouds and a breathable atmosphere. From this, we assume it to also have a surface water source and a biological source of oxygen gas. This could be from soil bacteria, which is assumed to be compatible with Earth-based life, since the film closes with a human colony populating Edmund's planet. Edmund shares many similarities with Earth: similar gravity, breathable air, arable soil, and potentially liquid water. It doesn't appear to be tidally locked either. Some Interstellar fans compare Edmund's to an ancient Mars back when it had oceans. We could also compare Edmund's to Kepler 452b, an exoplanet about 1,400 light-years away in the Cygnus constellation. Announced in July 2015, it's one of the most Earth-like planets identified in terms of its potential for habitability. It orbits a G2-type star just like our Sun, and lies in its habitable zone. It has a diameter 1.6 times that of Earth, and orbits its star in 385 days. Though we don't know whether Kepler 452b has fertile soil, clouds, or surface water, it seems remarkably similar to Edmund's. Kepler 452b is thought to have a rocky surface with a possibility of liquid water, much like Edmund's planet, which is shown to have continents, oceans, and potentially lush vegetation. These features indicate that both planets might support complex ecosystems. What's more, both planets are thought to have atmospheres capable of supporting human life. Kepler 452b's potentially thick atmosphere could sustain liquid water and regulate temperatures, similar to the breathable atmosphere shown on Edmund's planet. By the end of the film, Edmund's planet is shown as a viable option for human colonization. Kepler 452b also represents a potential target for future human exploration and settlement. We just need to develop hypersleep pods and find a nearby wormhole first. But let's move on from Edmund. We have the strangest, most mind-bending scene of the whole film to explore. The part where Cooper enters the black hole. In a bid to save the mission and to get at least some of the crew to the final planet, Cooper has to sacrifice himself, catapulting himself into the heart of the black hole to give others enough momentum to escape its gravity. Ironically though, this isn't the certain doom it first appeared. At the heart of the black hole, Cooper finds a tesseract, a representation of 5-dimensional space, where time is a physical dimension that he can move around in. He's able to use gravitational forces here to reach out to his daughter back on Earth across space and time, and bizarrely is able to give her the knowledge she needs to start the mission to the other planets in the first place. So let's ask the big question here. Is any of this theoretically possible? Let's start with simply the concept of entering the black hole. You may be surprised to hear this, but black holes are actually quite hard to get into. Angular momentum can become near relativistic the closer you are to the black hole, requiring you to shed momentum before you can fall any deeper. That accretion ring in the film, around Gargantua, is matter that is doing exactly that, spinning so fast as it tries to shed momentum to fall deeper into the abyss that the friction involved has turned it into a bright plasma. Seeing as this plasma can reach temperatures of millions of degrees Celsius, this might prove fatal for poor Cooper. But let's say that Cooper manages to find a route that does not turn him into superheated plasma on the way in. What would happen? Firstly, as he crossed the event horizon, the boundary after which even light can't escape, the light bouncing off his body would make it appear as if he were moving slower. If you were viewing this from the outside, you'd see the image of his body freeze and persist on the event horizon before gradually turning invisible. Because the light is being stretched by the extreme distortion of space-time, its wavelength would increase, and the light you receive later on would be more and more redshifted, until Cooper vanished from your view entirely. Cooper, meanwhile, depending on his angle of entry, would start to experience an effect known as spaghettification. Essentially, as parts of his body started to experience the passage of time slightly differently due to the gradient of gravity he was falling into, he would find himself slowly becoming more and more stretched. This pull would eventually snap him in half as the force of it overcame the bonds between his molecules. This would happen again and again until he was just a stream of molecules falling into the black hole's heart. This would not necessarily happen exactly at the event horizon. The event horizon itself is not truly a physical object, but rather is simply the mathematical point between gravity that is escapable and gravity that is inescapable. Cooper might not notice he was crossing it, if it weren't for an obstacle known as the photosphere. There is a point in space along the edge of the event horizon where gravity pulls just the right amount to not let any light escape the black hole, but also doesn't pull enough to drag it in deeper. In effect, at this precise distance from the singularity, any photons of light that arrive enter an orbit they never leave. Over time, the amount of light here would gradually increase and increase. Most likely, when Cooper entered this specific zone, he would suddenly encounter a previously invisible, massive spike of radiation that could very easily kill him, assuming he wasn't already dead from the accretion disk's plasma, or the spaghettification. There are lots of ways you can die when falling into a black hole, but let's say that he manages to get past all of that. Could he then actually attempt that last point, to speak across time and space using gravity? Honestly, it's a little unclear. The physics beyond the event horizon is murky at best, so scientists don't really know for sure what happens down there. But strangely, it does bear some passing resemblance to our current mathematical solutions on the subject. Our maths, as it stands, says that space curves so much that all the paths you can travel just lead you down deeper into the black hole. But there are some weird scenarios where you can end up arriving at points in your own past, which could allow you to influence what you do there. Which brings us once again to the idea of paradoxes. Paradoxes are all through the film Interstellar. What if Cooper did something in the black hole that killed his past self? That's 4 kinds of dead now, for those keeping track, thus stopping himself from going back in time later. Then he would never have gone back to kill his past self, thus saving his past self's life. But that would mean he was able to go back, so could kill himself. and on it goes in a circle. The film attempts to get around this circle using something known as a bootstrap paradox, where everything in the film always happened the way it was once it was influenced through time travel. Cooper used the black hole to teach people back on Earth data that they needed for a gravity equation, which allowed them to launch Cooper's ship in the first place. But the film showed that Cooper's interdimensional fumblings were present at the start of the film too. Cooper did what he did, and he had always done it. In a way, this closes the loop. But this is a little unsatisfying, as it still opens the question of what would have happened if Cooper had decided not to share gravity equation data with the past. It removes free will. As soon as Cooper realized that he was in a bootstrap paradox, he had to do what he'd always done, or the whole thing would collapse. This happens even more broadly as we learn that future humans, now sufficiently advanced, were the ones who created the Tesseract that allowed humans to be saved in the first place. But what if they decided to not create it? Then we're back in paradox territory, where the universe has to solve a thing happening and not happening at the same time. We don't really have an answer in physics for what happens with that. So this is an area where Interstellar becomes less scientifically certain. However, it does make for a mind-bending story. In the end, despite some divergences from science taken for dramatic purposes, Interstellar helped showcase the fascinating concepts from modern physics to a mass audience. It was able to show how time isn't just a rigid arrow, but rather, as the Doctor said, a wibbly-wobbly, timey-wimey thing, going at different speeds depending on what gravity fields you were moving through. Overall, the film did a pretty good job of trying to remain scientifically accurate. A few creative liberties were taken to enhance the storytelling, but that's why we go to see a sci-fi movie instead of a lecture. The power of science fiction is its ability to make us dream. And even though we are very far from colonizing other Earth-like planets, Interstellar does just that. It encourages us to keep that spark of wonder alive. Maybe there's someone out there looking longingly out at us too. Well, that's all we have time for today. I hope you've enjoyed listening to this podcast exploring the science of Interstellar. If you like what you've heard, please feel free to follow us for more podcasts on other fascinating space topics. But for now, I'm Alex McColgan, and this has been Astrum. All the best, and see you next time.